Welcome back. My name is Chris Pullier, and I am a measurement scientist and a data scientist. And in this video, I want to tell you how there was an area of land in Virginia called Back Bay that was almost at the brink of disaster. And so I want to tell you the story from the end, which is the underwater grass beds are returning as our populations of largemouth bass and other fish, water birds are now able to use both the impoundment complex and the Back Bay for habitat. Now, the impoundment complex was an area of land that they had to designate to try to give these animals, the birds, some fish, a refuge within the entire Back Bay that was a little bit cleaner, because there was a time here where this area was highly contaminated due to a lot of the land changes in these surrounding areas on the east side of Virginia. Now, this is interesting because I was just looking for data to help me explore what's going on in the world through the chemical lens, but kind of in a way that might flow under the radar if you're not just searching for it. And I don't know if you're aware, but data.gov is a federal website that allows you to access federal data or different state or municipality data. And so I was just searching through here and I came across this data set here from ServCat. This is from U.S. Fish and Wildlife Services. And you can see here, let me make it a little bit larger, the water quality data for the refuge collected by volunteers, collected once every 2 weeks. And we have turbidity, pH, dissolved oxygen, salinity, and temperature. Sampling will occur at designated locations in the following bodies: the bay, D pool, C pool, B pool, and A pool. And here is the reference for this. And so this is great because this is available to us. It's going to cover several years of testing in this region. And we can see how they have these conclusions that the water is now better. It's not pristine, but now because of the actions, the corrective behavior, we're able to repopulate and see that ecosystem reemerging. And here's the data that tells that story. Now, of course, in this channel, I walk through data using Python. So that's what we're going to do. We're going to download this data set, and I'm going to walk through just a very simple way we can visualize this story and see the improvements that are happening. In particular, we're going to focus on salinity, as this was a huge factor in improving the overall water quality. And we can see how that is now beginning to decrease due to the efforts of many of these volunteers and agencies in the area. So this is what the data looks like. We have our site ID, which are the bay, and then they told us they have several pools: A pool, B pool, C pool, D pool. We also have the read date, which is this timestamp here, as well as the salt levels in parts per trillion, dissolved oxygen, pH, depth, water temperature, air temperature, the time of measurement, the tech that was performing the measurements, and just a few other information that's useful, as well as the year that the data was collected. And so with this looks like a typical data set, which means we can use a lot of our typical work processes for understanding this data. Now, there's no need to do anything overly sophisticated, but this is a great way to see real world data in action and understand how this data matches the story, or perhaps doesn't, that we're being told about this body of water. And again, I think this really shows the importance of measurement science in the real world, data science in the real world, and the positive impacts that the people who surround this and add the context can have. So I'm going to read the data in. I've imported some of the information. So if this is all you're seeing, I have the reference, I have a link to that data set, and this is where I've stored the data locally. And so I'm going to run that, and then I'm going to begin the rest of my notebook. So I'm going to use Pandas, Seaborn, and Matplotlib. These are common data science libraries for reading and data with Pandas, and data visualization with my Seaborn and Matplotlib imports. To begin, I'm going to read in the data that I have in this path here. Now, I always use R to ensure that this string is treated as a raw string. Sometimes when you don't have that, there's special formatting, particularly with your front slashes or back slashes, that could change how the interpreter reads that string. And so to ensure that it's reading as a raw string, I just use R both on my Mac and my PC, my Windows PC. So to begin, I'm going to use read CSV, as this is a CSV file. You can tell by this extension there. And then I'm going to begin doing some data cleanup. I have my read date that I want to treat as a date time object. So I'm going to use pd.toDateTime and convert this into a date time instead of a string as it's going to read in. And then I'm going to drop the years column and anything that doesn't have a date there. So there might be some data that doesn't actually have the read date. And I want to ensure that we're going to subset based on that and then drop any of those rows that are missing there. And then we're going to set the index to read date. We're going to sort and then just select the numerical data from this data set. I'm going to run this entire cell and show you what we get at the end. So this cell has now run. I'm going to show you the data there. Here are the first 5 rows. You see there are some data that are missing because some of the measurements were created incredibly early in the late 80s, whereas the salt measurements did not occur that early in the data. If we look at the data types, I am selecting just the numerical data, which is important because I want to just visualize this data. I don't care too much about who was collecting. That's maybe more for the folks who are creating these experiments in real time. And so I want to plot this overall data, and I'm going to do that using the plot method in the pandas data frame library. I'm going to use subplots equals true argument. That way I will create a new subplot for each of the columns. So this is done automatically. This is one of those nice things about how these libraries interact with each other. And so when I say subplots equals true, each column will get its own plot. So we'll just have a column of the salt data, the dissolved oxygen data, the pH data, and then we're going to set the figure size of 10 by 12 and then assign a title. Next, I'm going to use the sns.dspine to help clean up the figure just a little bit, and then plt.show to render that figure to the screen. When I run that, you see that this is what the data looks like. So in the beginning, they were not collecting the salt data. You see we also have some gaps in those measurements. However, this is still a decent way to visualize the data. This kind of gets a hint at some of the messiness that occurs. Maybe there were some samples that were missing, data that had some erroneous figures that they removed. And thus, this is not too unexpected considering the length of time. So the first measurements were collected in the late 80s for some of these experiments and all the way up into the 2020, late 2010s into the early 2020. And you can see that the salt levels have gone down. There are some spikes here, but it's also really noisy. There's a lot of jagged features in this data, which may or not be truly representative of the trends that are occurring within the changes that are happening in this ecosystem. Now, there's some context around, maybe currents and other domain-specific things, but I would tend to say it's important to maybe add and rolling average to this data. So what happens if we actually take 20 data points, average that and treat it as one data point, and we're going to move that window down to create these rolling averages across this to just help us smooth out some of these jagged peaks and see what the data might be telling us with less of that noise present. Again, to do that, that's really simple with Python and pandas. So I'm going to create a new data frame called df_rolling. I'm also going to fill in any of the missing values. So if there's a missing value in the data, I'm just going to fill it in with the mean of the data set, the average of the data set. And then we'll use a rolling window of 15, which doesn't actually perform the aggregation that we want. So we then define we want the mean and then drop any missing values. And I'm going to plot that rolling data. And so here you see we're chaining several methods. And if this is not the way you prefer to see it, but you want to see it on separate rows, of course, if we put everything in parentheses, we can separate it by row. And it's very easy to now visualize all the transformations that are happening in this chained method. And then, like I said, we're going to plot, we're going to use subplots, set the same fig size, 10 by 12. We're going to update our title, dspine, and use plt.show to render that figure. When we do that, you can see we can observe more patterns within the data because we're now using our rolling average. You can see that these salt values has some periodicity at the beginning. It continues, but you can see that overall the values are significantly lower towards these later dates than the earlier dates. Also with dissolved oxygen, we also see some patterns here. And this is where some of that domain expertise would really come in handy with folks who understand the water in this area, the environment in this area. But based on what we could do with just processing this data without that expertise, we can still get some interesting insights. Furthermore, we can see that the water depth has also oscillated some. Perhaps there is something with the instrumentation or different currents that were really moving the water and changing the type of water that was present in the bay at the time. The air temperature has also been oscillating, but this is to be expected as they're measuring at different times of the year, different times of the day, and we're just averaging all of that together. Furthermore, I mentioned that they were sampling at different points in this bay. Now we're just averaging all that together to get a single measurement at a single time point. But there are other ways that we also could break this down if we were to dig even deeper into this data. But I think when it comes to understanding their claim that overall the water is cleaner, it's more conducive for wildlife, we can really see that story through the salt data, this salinity data, that yes, overall, over the past 20 years, the salt levels have significantly decreased. And thus, this is why we can now be confident that the underwater grass beds are returning, as are the population of largemouth bass and other fish. Now, admittedly, they are saying that this is not an ideal state, and we can tell in the data that there are some things that are increasing at the end. But with this, we can now see how the interaction of our measurement science, our data science, and these real-world applications really comes to life using Python and the domain expertise that we have. If you like this style of content, I will create more. Like, comment, subscribe, and I'll see you in the next one. Peace.